So here is our note sheet from last class. We left off in last class where we were using trig to find a side length or an angle. So let's see, we had problems like these where we were finding, we had the cosine of 60 equals 8 over x, and then we use that to find a side length. And then the problems down here where we had to use an inverse trig function to find an angle. So remember, whenever you're trying to find an angle, we need that inverse. So like down here, we had to do the inverse tangent of 8 over 9 to find the measure of that angle. So this is what we were doing in our last class. We had a couple of word problems there. Well, today's focus, it might seem different, but these concepts are definitely related. We're going to talk about special right triangles. In fact, we already did a bunch of special right triangles when we started class. And that is when you have triangles that are isosceles and right all at the same time, like this triangle here. Okay, it's isosceles and a right triangle. And so we name that, it's a special right triangle, we name it by its angle measure. So that would be a 45, 45, 90 triangle. And if you have a 45, 45, 90 triangle, there's a shortcut that you could use to find the side lengths. And the shortcut is that if you have one of the legs, let's call it x, we know it's isosceles, so the other leg has to be x also. And if we did a little Pythagorean theorem work, our hypotenuse will always come out to be that number x times the square root of 2. And so for a 45, 45, 90 triangle, we have x and x and x square root of 2. And that saves us time. So like if we have one of those sides, we could find the other ones very quickly by using that little formula. So for example, in 1a, we have one of the legs is 6. And now this is isosceles, which means that side and that side are congruent. And so that means that this side would have to be 6. And now instead of doing the Pythagorean theorem, I know it's a 45, 45, 90 triangle. So that's going to be 6 root 2. Okay, it's x and x and x root 2. So for 1b, the only difference is we're given the hypotenuse. This is our x root 2, which means our x is 14. So that means that the side lengths are 14 and 14. So pretty quick problems if we recognize it's a 45, 45, 90 triangle. The next ones get a little bit harder. So in part C, it is also a 45, 45, 90 triangle, but recognize that, this is our x, x, and x root 2, but one of our sides, our x side, this, just looks a little different, right? But that's okay, because this side and this side will be congruent. So this is 10 root 6. And then the hypotenuse will be 10 root 6 root 2. Sorry, my screen is really lagging, my display screen up there. So that's going to be then 10 root 12. Well, root 12 can be, if we did a factor tree, is going to be 2 root 3. So I have 10 times 2 root 3, ultimately giving me 20 root 3 for our hypotenuse. So definitely a little more work there, but we didn't have to do the Pythagorean theorem at least, and square both of those 10 root 6s and then take the square root. All right, are you still with me? Because the next one gets a little harder also. The problem with part D is that we're given the hypotenuse here is 14. Well, remember, this is x, and this is x, and this is x root 2. So to find our x's, what we want to do is set our hypotenuse equal to x root 2 and solve it for x. So that's going to be 14 over root 2, which of course I'm going to have to rationalize, right? So now x is 14 root 2 over 2. Better known as 7 root 2. All right, so that means my two legs are 7 root 2. And again, looking for shortcuts today, there's definitely a relation here. If we take 14 and cut it in half and might write it as root 2, those sides are 7 root 2. So like if this was 20, those would be 10 root 2. Okay, and that's, again, if you think through the algebra as to how that would work each time. All right, any questions on 45, 45, 90 triangles? All right, well, the second one, and we didn't talk about these earlier, is a 30, 60, 90 triangle. And again, they're named by their angle measures. So the angles are 30 degrees, 60 degrees, and 90 degrees, which of course adds up to 180, right? So if you have a 30, 60, 90 triangle, the relationship between the sides would be this. The side across from the 30, let's call that x as some given number. And that's the short leg. Okay, because it's across from the smallest angle. So if that's x, the hypotenuse will be twice its size. It will be 2x. And the longer leg will be x times the square root of 3. So we have x, 2x, and x root 3 for our 30, 60, 90 triangles. So using those shortcuts, looking at 2a, I'm going to erase this in just a second, but that's x, that's 2x, this is x root 3, meaning like my x is 4, okay? So that means then for my sides, my short leg is 4, and the hypotenuse would be 8, would be twice that. So we're really trying to look for those shortcuts. In 2b, we're given the hypotenuse is 12. Well, that means that the short leg has to be half of that, because the hypotenuse has to be twice the short leg. So that bottom is going to be 6, which means the right side or the longer leg would be 6 root 3. So those are some basic ones. The next one will be a little harder. Are there any questions on A and B before I move on? All right, well, let's take a look at C. The difference is C, this is our longer leg here. Remember, this is x, this is 2x, and this is x root 3. But it's a whole number. Okay, so our x root 3 is equal to 3, and we then need to solve that for x. So I'm going to do that algebra down here. X root 3 is equal to 3. And so x would be 3 over root 3, which of course I'll rationalize. And so I've got 3 root 3 over 3, which then is the square root of 3. So we had to do a little work there to figure out our x, but now I know the length of the other small leg is the square root of 3, and the hypotenuse is twice its size, or 2 root 3. And for part D, we're given the hypotenuse. The hypotenuse is 10 root 3. Well, remember the relation between the hypotenuse and the shorter leg. The shorter leg is half the hypotenuse. So that means that this would be 5 root 3. Okay, half the hypotenuse. And then the longer leg is this number times the square root of 3. So it's 5 root 3 times the square root of 3, which is 15. So they are shortcuts, but we do still have to do a little thinking there, of course. And those are the two special right triangles that we're going to focus on, the 45, 45, 90 and the 30, 60, 90. Are there any questions? I got more for you guys. Okay. So let's apply them to a couple of problems here, okay? So for 3A, we're trying to find these lengths. So the first thing I would say is we can't just find y right off the bat, but I do recognize that we have a 45, 45, 90 triangle here. And since my hypotenuse is 12 root 2, that means my legs are both 12. And now that gives me the longer leg of that 30, 60, 90 triangle. Now remember, this is x and this is 2x, and that 12 is our x root 3. So that means that to find our x, I have to do 12 equals x root 3. I'm solving that for x. So x equals 12 over root 3. Which then rationalized is 12 root 3 over 3. Or 4 root 3. So 4 root 3 is going to be the short leg of that 30, 60, 90 triangle. And then the hypotenuse is twice that size. So our final answer is that y is equal to 8 root 3. Okay, part B. We have kind of a crazy looking figure here. So let's try and figure out, where do we start? Well, we know we're given this side, which is part of this triangle. And so let's look at that 45, 45, 90 triangle. Well, 8 is the hypotenuse. And so 8 is our x root 2. And if you remember, that means that the legs are going to be half of that root 2, if 8 is the hypotenuse. Well, now that 4 root 2 is the hypotenuse of that guy.
of that 45, 45, 90 triangle, which means those legs have to both be 4. And if those legs are 4, this 4 is the hypotenuse of that 45, 45, 90 triangle, which means its legs would be half of it root 2 or 2 root 2. And that's the hypotenuse of that final triangle, which ultimately tells us that y is equal to 2. So lots of 45, 45, 90 triangle work there. All right, the next part kind of, leading to answer the question of, well, why study these triangles? Why a 45, 45, 90 and a 30, 60, 90? Well, because they come up fairly frequently, and that's because if you take a square and you cut it in half, you get a 45, 45, 90 triangle. Okay, so it's a fairly common shape to come up with. It's half a square, a 45, 45, 90. If you take an equilateral triangle, now remember, equilateral means all the sides are the same or congruent and all the angles are congruent. That means that all of these angles are 60 degrees. Well, if you drop in an altitude, remember an altitude is a segment from a vertice perpendicular to the opposite side, we end up with a 30, 60, 90 triangle. Okay, so a 45, 45, 90 is half a square, and a 30, 60, 90 is half of an equilateral triangle. And so in the big picture of things, we'll then apply this to what's called the unit circle. Now, unit meaning 1. So the unit circle has a radius of 1. Well, I know that a circle has 360 degrees. That means that half a circle is 180 degrees. So if this is 210 degrees, that means that this little guy right here has to be 30. Okay, 180 plus 30 would be 210. And I can draw a perpendicular to the x-axis, giving me a 30, 60, 90 triangle in the unit circle. And we're going to put that to a lot of work later on, not today necessarily. Okay, but just to give you a little preview, like problem number 4, if we wanted to find the coordinates of an angle rotated 315 degrees. Well, first let's figure out where 315 degrees would be. Now I know that a full circle is 360. Do you remember your quadrants? That's the first, second, third, and fourth quadrants. So what quadrant is 315 degrees in? Come on. You have a 25% chance of guessing. Yeah, it's in quadrant 4. So 315 degrees is less than 360, so it's going to be somewhere around there. So if I draw in an angle, here's where that triangle stuff applies. If this is 315 degrees, that means that this guy here must be 45 degrees, 360 minus 315. And so if I draw in a perpendicular to the x-axis, I have a little 45, 45, 90 triangle here. So I'm gonna blow that up and just draw it bigger over here on the right. So here's our 45, 45, 90 triangle. Remember, it's the unit circle. That means that this is 1. So our hypotenuse is 1. So if this is 1, then the legs are half of that times the square root of 2. So it's 1/2 times the square root of 2, which is root 2 over 2. So if we're looking for the actual coordinates down here, we're going to go to the right root 2 over 2 and down root 2 over 2, meaning its coordinates, our x value is root 2 over 2, and our y value is negative because we went down root 2 over 2. So that would give you the coordinates of that point at 315 degrees of the unit circle. All right, I threw a lot at you on that problem. Are there any questions on it? All right, we've got one more here. All right, we want to find the exact area of a regular hexagon. Okay, that word regular, that means something. In math, it means that it is equiangular and equilateral. So all the sides are congruent and all the angles are congruent. So I'm going to do my best to draw a hexagon here. 1, 2, 3, 4, 5, 6. It's not what I wanted. I don't know if it'll snap in a hexagon for me or not. I'll give it another shot. There we go. All right, we're going to find the area of this. We know that the perimeter is 90. So if I want to find the area, the first thing I'm going to do is I'm going to split it up and think, all right, there's a triangle. And if I, connected all these, I would have 6 triangles. Which means if I found the area of one of these guys and multiplied by 6, that would be the area of the entire thing. So I want to find the area of one triangle, but then I have to multiply by 6. So let me draw that blue triangle over here. And let's write down some things that we know about it. If the perimeter is 90, that means that all these sides added up is 90. There's 6 of them. So 90 divided by 6, that'd be what, 15, right? So that means that the base of this is 15. I also know that since there are 360 degrees in a circle and there's 6 interior angles in there, they all must be 60 degrees. So that means that this top angle here is 60 degrees. And in fact, it's isosceles, which would then mean that the base angles are also 60, making it equilateral. So lots of geometry coming back here. But what we have, if we draw in our altitude, is we have a 30, 60, 90 triangle. And in that 30, 60, 90 triangle, our short leg is 15 halves. The hypotenuse is twice that, which is 15. That makes sense because the big triangle, the blue triangle is equilateral. And the height of it is the base times the square root of 3, or 15 root 3 over 2. So now I have all the information I need to find the areas. So to find the area of this shape of the original hexagon, I'm going to do the base, which is 15 times the height divided by 2. That'll give me one blue triangle, and then multiply by 6. So the base is 15 times the height, which is 15 root 3 over 2. So that's base times height divided by 2. And then I have to multiply by 6 because there are 6 of those. And so at this point, we could plug that into our calculator, get an approximation. It would be approximation because we have that square root of 3 hanging in there. Or an exact answer. Let's see if we can do some work here. I can reduce my 6 and 2, make that 3 over 1, right? And 15 times 15 would be 225 root 3, and then over 2, and then times 3, giving me a grand total of 225 times 3. That would be, well, 200 times 3 would be 600. 25 times 3 would be 75. So that's 675 root 3 over 2. And that would be the area of the regular hexagon with a perimeter of 90.